Hello, my name is Justin Greathouse. Today I'll be presenting materials of the future for use in nuclear power. I chose to focus my research on high-strength ceramics, so that is what we will be talking about today. So first, how do we say what materials we will be using in the future? It's almost impossible to really say. New materials are constantly being researched, constantly being tested, constantly being developed. Colleges everywhere are looking into the uses of graphene and single string boron. There's all sorts of awesome materials that are coming out in the future. For this project, I chose to look into things that currently exist and things that are on the close horizon to being used in mass applications. These applications not only include nuclear, they also include space travel and in use of engines. A lot of the research that's driving the high-strength ceramics is the use in more efficient, higher temperature engines. So that is what's driving the field, more or less. So why do we need new materials for use in nuclear power? Nuclear power has kind of seen a stagnation in use and in technological growth, due in part to the limits of the materials that we use. A lot of the future technology is looking for a higher temperature, more efficient reactor. The issue that we run into with higher temperature reactors, however, is that we run into problems with corrosion, problems with yield strengths, and things of that nature. So we need to find materials that fit into this unique nature that reactors provide, such as high temperatures, high pressures, irradiation of materials, resistance to corrosion. So what makes a good material? When talking about nuclear power, we always are looking for certain properties, and then we have certain properties that we can vary by application. Properties that we always desire would be the ability to withstand high heats and high pressures, show a high strength, show the ability to resist fracture, resist corrosion. Thermal conductivity can go either way. For use in heat transfer surfaces, we want high thermal conductivity so that we can transfer that heat with very little losses in the system. For applications such as piping and pressure vessels, things of that nature, we want very little heat transfer to occur so that we can maintain the heat within the system. This will allow us to improve efficiency because we have less losses to ambient. This is why I propose high-strength ceramic as the material of the future for nuclear power. Some of the desirable properties that high-strength ceramic has is a high strength, a relatively high fracture toughness, high hardness, very resistant to wear, very resistant to friction, anti-static, non-magnetic, low thermal conductivity for some alloys and high thermal conductivity for others, very corrosion resistant as it is a very basic alkaloid. The modulus of elasticity very similar to steel, and thermal expansion coefficient is very similar to cast iron, so we don't have to worry about losing clearances by it expanding when it gets warm. Fracture toughness itself is considered the ability to resist fracture, especially in the presence of a Fracture toughness itself is considered the ability to resist fracture, especially in the presence of a flaw. Included are two pictures of a structural steel that has undergone indentation and a ceramic that has undergone indentation. You can see in the picture of the steel that cracks have started to form at the corners of the indentation, whereas in the ceramic, no cracks have begun to form. This is especially important because ceramic is typically associated with being a very brittle. For resistance to corrosion, ceramics are typically metals that have undergone chemical reactions to make special alloys. This allows them to be much more resistant to corrosion than most metals are, especially in extreme environments. For metal systems, the chemistry needs to be constantly monitored and maintained in order to prevent corrosion and deposition of sludge and buildup of chemical deposits and everything. With ceramic, that's much less of a concern because we don't need to monitor chemistry so much, since corrosion is no longer a concern. The creation of wear products not so much of a concern anymore. The big benefit of this is it allows replacement parts over time to be minimized. This increases uptime, cuts overhead down a lot, so that saves a lot of money, which is always of importance in any business model. Thermal shock is another consideration that goes oftentimes into the conversation about brittle fracture. There's always heat up rates and cool down rates associated, where exceeding those rates increases your chance for brittle fracture of your material. One of the big benefits of ceramic is it has a very impressive thermal shock. It can receive a decrease in temperature of 250 degrees Celsius or an increase in temperature of 800 degrees Celsius very, very rapidly, therefore preventing brittle fracture, which is always a concern for ceramic materials. As I mentioned before, thermal conductivity for ceramic can vary depending on the alloy that is used and the specific application that it is being used for. You can either have a thermal insulator or a thermal conductor as necessary, depending on, like I said, the alloy. There are two big alloys that I found in my research, the first being aluminosilicate. It has a thermal conductivity of 1.3 watts per meter Kelvin. And then the other is aluminum nitride, which has a thermal conductivity. It's a range, but it's approximately 125 watts per meter Kelvin. Steel itself has a thermal conductivity of 43 watts per meter Kelvin, where stainless steel has a thermal conductivity of 16 watts per meter Kelvin. So, for use in both insulator and conductor, depending on your type of ceramic that you are using, you can greatly improve heat transfer or greatly reduce heat transfer over the use of steel, which is the most commonly used material. The primary negative of ceramic is that in creating a material that has such a high strength and resistance to high pressures, you lose the ability to be a ductile material, causing it to be more brittle than, say, metal would be. A lot of research that is being done by material colleges around the country is to, as you'll see on the stress-strain curve, move that break point further down the strain line. There are several different ways that they are accomplishing this. One of the ways is to layer fibrous material between layers of ceramic so that when the ceramic starts to reach failure, the fibrous material fills in the gaps, allowing for strain to occur, and then when the stress is removed, it moves back down the line and you do not have failure. Another way is they have a honeycomb lattice structure that they are using for ceramic that they have actually been able to compress and then remove the pressure, and it regained its original shape. Both of these are in early research and development and not ready for applications in a commercial nuclear plant. However, since we are talking about applications, materials for the future, these could be something that are considered down the line 5-10 years from now. So in conclusion, while ceramic is not the perfect material, we don't know what the future is going to hold. In my personal belief, ceramic does offer the best that we got for the near future to use in higher efficiency, higher temperature, higher pressure reactors, as well as space travel, engines, anything that requires a harsh environment, anything that irradiates or causes corrosion. Ceramics tend to outperform steel in pretty much all categories, with the exception of the ability to strain under a given stress. This is why I feel that ceramic, in the long run, if we were to use it in nuclear power with some of the new technologies that are coming out for molten salt cooled reactors, superheated CO2 or superheated helium secondary systems, where as temperature increases, so does efficiency. I believe that we will overall reduce lifetime costs of the reactor. We will increase efficiency, increase reliability, and set the future up to be a more efficient world reliant on nuclear power.